So, as has been mentioned several times now, we have three great keynotes for you at this meeting. I'm very pleased to announce that the first one is going to be Martin Russell, many of you know from the University of Birmingham. Martin has been in the field for exactly as long as me. No, not quite true. Not quite true. Professionally, let's say. We started pretty much at exactly the same time in 1980 at the Raw Signals and Radar establishment, and subsequently the Speech Research Unit. And Martin joined our team and really made a huge difference, because at that time we were lacking some serious mathematical expertise in the field. And Martin came along and brought that, and really made a mark in some of his early work in duration modelling, segment modelling, and the like. He joined Birmingham University as professor in 98, where he's built up a lovely team. I visited them only the other day, and I see a lot of familiar faces here. He's got some great students and support there. And he's been working in a number of different areas, but one of the areas which he has been specialising in, which I think is of great importance to our field, is children's speech. So he's going to talk about speech technologies for children. Over to you, Martin.
Okay, thank you very much. Roger's being very modest, because the only reason I started working in this topic is because when he was asked to set up a research group at what was then RSRE, he stipulated that he wanted a mathematician, and I just finished my PhD and I was looking for a job, so that's how I ended up working in speech technology at all. So he's definitely been working in the area for longer than I have. So I'm going to talk about speech technologies for children, which is an area that I've been active in at Birmingham, and also when I was at the Speech Research Unit at RSRE. I'm going to say a few words briefly about applications, and then I'm going to talk a bit about the history of speech recognition for children. And then I'll spend a considerable amount of time trying to give some opinions on to why I think speech recognition is particularly difficult for children's speech. And there are the physiological differences between children and adults, vocal tract lengths, fundamental frequency. I'm going to talk a little bit about some results on speaker and gender recognition for children, because I think some of those results throw some light onto the properties of children's speech as well. Look at the question about whether this difficulty of speech recognition for children's speech applies to all children, or is it just specific to some children. I'll say a little bit about that. I'll talk about bandwidth effects, which are also very relevant for children's speech. Then I'll talk a bit about human results of human recognition of children's speech. So hopefully by then, I'll have covered most of the field of why speech recognition for children is difficult. Then I'm going to talk a bit about the state of the art. This is not my own work, this is work that other people have done, but I'll tell you about what people are doing applying DNN systems to children's speech. There are two particular studies that I'm going to talk about. And then I'm going to talk about some stuff we've been doing at Birmingham more recently, which is about looking at the effects of language acquisition, and how phenomena which are associated with language acquisition can or cannot explain some of the difficulties we have with speech recognition for children. So that's what I hope to get through. Some acknowledgements. These are just people I've worked with on children's speech recognition. So there was a group at RSRE, at the Speech Research Unit, Adrian Skilling, who's now at Apple, Kate Brown and Julie Wallace. And then a whole group of students who've been at Birmingham, and some still are at Birmingham, who've worked on this particular topic. And I'm going to quote from their work at various points in the talk. So, why is speech recognition for children particularly interesting? I think it's interesting because it has some really nice applications. So all of the applications that we associate with speech recognition for adults, we can also transfer to children, with a few exceptions. But there are some specific applications which are very specific towards children. Interaction with robots isn't just specific to children, interaction with avatars, but there's a huge amount of work on looking at speech technology with autistic children and encouraging communication skills with autistic children. There's also a lot about educational applications. Computer-assisted language learning is applied to adults, but has lots of applications with children, mainly with their own first language. Computer-assisted pronunciation training, trying to identify diagnosed pronunciation issues when they arrive, diagnose them early, and then to try and develop technologies for helping to correct pronunciation issues. Interactive reading tutors is a long-standing application. There have been projects in that area since the 1990s. And I think there's a new area where there really isn't very much activity, which is interactive dialogues for education. I think most of us have had the experience that when we verbalize a problem, somehow it makes that problem easier to solve or easier to address. And I think there's some really interesting potential of applying speech technology to try and exploit that phenomenon. And in particular in the STEM areas, speech technology, science, technology, engineering, and mathematics. That's what I mean. Speech technology. Sorry. Okay, so when did I start working on speech recognition for children? We had a project called the STAR project back in the 1990s. We just built a system called the Armada system. It was a speech recognition system, one of the very first real-time continuous speech recognition systems in the UK and in the world. And it got some publicity in the local press. And we were approached by Hereford and Worcester Education Authority to find out whether the technology which we developed for speech recognition could also be applied to pronunciation tuition for 5 to 7-year-old children, for primary school children. So this was quite forward-looking at the time, but it was a new application. And as I say, it came from the Education Authority. We built a real-time system. It ran on an Acorn Archimedes, which was the standard 1990s UK primary school computer. There's one in the right-hand picture. It was trained on children's speech. There were other systems out there, like reading systems, but they were trained on, the speech recognition was trained on adult speech and didn't work particularly well for children. So this was the first, my sort of introduction to the area of speech recognition for children. But things have moved on a lot since then. So this is this girl here. She's moved on. She's now got a degree in neuroscience. And hopefully I can persuade you that the technology has moved on as well. So that's what I'm going to talk about for the next few minutes. So historically, for me, the first paper that I read about speech recognition for children came out of Bell Labs in the 1990s. It was a paper by Wilpon and Jacobson. And it was basically looking at the performance of speech recognition for isolated and connected digits as a function of 5 different age groups. And they came up with a whole set of results, and I've tried to summarize them here. The first result they had was that if you train a speech recognition system on adult speech, then the error rates you get when you apply that system to children are something between 150% and 350% greater on children's speech than you would expect for adult speech. Well, that's not surprising because there's a big mismatch. The second point is perhaps the more interesting one. If you train the system on children's speech, so you have a matched system where the system is both trained and recognizing children's speech, then the error rates are still 60 to 170 times greater for children than for adults, compared with what you would expect for an adult on the same task. So, two issues then. First is the mismatch issue. If you train the recognizer on adult speech, then you've got a massive degradation in performance if you then try and apply it to recognizing children's speech, which I guess is not surprising. More worrying, if you can train the system in a matched way, so you train the system on children's speech, you still get very poor performance compared to what you would expect for adult speech. There's 2 comments on that. There are 2 factors going on here. One factor is that it's children's speech, but you'll see later on that bandwidth is important for recognition of children's speech. And so the fact that this was at Bell Labs and the fact that they did all of this over the telephone network will also have had an effect on the performance of the system. And I'll talk a bit later about what the effect of bandwidth is on speech recognizer performance. So there's a sort of another remark here. What this tells you is that even if we could develop normalization techniques so that adults trained speech recognition would work equally well on children as a matched system, there would still be a big gap between the performance which we would observe and the performance which we expect to get from comparable systems trained and running on adults. And that's sort of summarized in the next slide that I've got. This is sort of these bars here. So this is a schematic picture. It's not a result of any particular experiment. So this bottom column, this bottom row, is supposed to represent what you might think of as the standard situation with speech recognition. This is a system trained on adult speech and tested on adult speech. And the top row is the same system trained on adult speech but tested on children's speech. And this is the 300% increase in errors that Jacobson and Wilpon talked about. And the second row, the middle row, is when you train the system on children's speech and you test the system on children's speech. And most of the research that I'm going to talk about, which happened sort of in the 1980s and the early 2000s, is basically trying to bridge that first gap. It's trying to take adult speech recognition systems and find normalization techniques which, when you apply them to children's speech, give you performance which is comparable to that which you would get if you trained the system on children in the first place. That's been the focus of research. I think what's more interesting is this second challenge, which is, suppose that you train the system on children, you test the system on children, even under those circumstances, which you might think of as ideal circumstances, the performance is still not as good as you would get if you trained and tested a system on adult speech, if you can imagine keeping all the other variables constant. And so it seems to me the more interesting challenge at the moment is this bottom one. How do you take matched speech recognition systems, where even if you have training data and test data from children's speech, and how do you make the system perform as well as the comparable system running on adult speech? And I think that's the interesting question at the moment. So why have people focused on the first question? Well, it's sort of obvious. Most speech recognition research focuses on adult speech. Most resources are focused on adult speech. It's relatively easy to get a large corpus of adult speech to train your speech recognition system. It's almost impossible to find a large corpus of children's speech to train your system. Those corpora just don't exist. So there's been a natural tendency for the research in speech recognition for child speech to focus on how to make the existing adult systems work well for children. So why do I think, or why does anyone think that speech recognition is difficult for children's speech? And the most obvious reasons are the physiological differences between adults and children. And those are the differences which people have focused on when they've been trying to make speech recognition systems trained for adults work on children's speech. So the first obvious difference is that children are smaller than adults. They have shorter vocal tracts. And as a consequence of their shorter vocal tracts, important structure in the spectrum is shifted up the frequency domain. And so things like formants will occur at higher frequencies in children's speech than in adult speech. And so there's a natural mismatch between adult speech data and child speech data. But it's fairly clear how you might go about compensating for that, but I'll talk a little bit about that in a moment. The other issue is that children have much higher fundamental frequency than adults. And that's more subtle. That means that the information in the spectrum is more difficult to resolve, and I'll explain a bit more about that in a few moments. And again, that leads to higher error rates. And several authors claim that these are the two main sources of acoustic difficulty if you want to recognize children's speech using systems trained on adults. So for the next few minutes, I'm going to talk a little bit about these two particular issues. Oh, no, I'm not. I'm going to talk about this first. So these are some other sorts of variability. There have been several studies of acoustic properties of children's speech, specifically by Patamianos, Narayanan, and Lee, or other combinations of those authors, and also by Girosha and Giuliani from FBK in northern Italy. They've published several papers on acoustic properties of children's speech. So some of the differences between children's speech and adult speech, and some of the sources of variability in children's speech include longer vowel durations. Vowels are typically 30% longer in children's speech than in adult speech. Shorter consonant vowel transitions. The transitions between the consonant and the vowels are measured to be much shorter for children than for adults. And then there's a whole other range of acoustic variability. So when you measure spectral variation within the same vowel in child speech, the variability is much greater than with adults. The mean Euclidean distance between cepstra in the first and second halves of vowels is 20% greater in 5-year-olds than 12-year-olds. And inter- and intraspeaker variability increases as age decreases. And that's a standard thing you observe with all things to do with children. If you try and measure anything, the variability will become greater as the child becomes younger, and your error rates will increase as the child becomes younger. So now I will talk about how speech recognition systems try and deal with some of these differences. So here's a standard, very simple picture of a speech recognition system. It doesn't really matter what type of system it is, it will have these types of components. So the first stage, we take the acoustic signal, we apply some speech signal processing to it to try and convert the waveform into a sequence of feature vectors which preserve the salient properties that are important for recognizing speech, distinguishing one type of sound from another. And we apply some pattern recognition to that, and the ingredients in the pattern recognition include some sort of acoustic model, some sort of model of what the different sounds of the language look like in terms of those feature vectors, a language model, which is about the constraints on the order of the words that the user is likely to say, and a pronunciation model, which is to do with the way in which the words in the application are expressed in terms of the basic sounds, the phones of the language. So you're all familiar with that. But everything I'm going to talk about initially is all focused on this bit here, the signal processing part, because that's where most of the work on normalization has taken place. So here's a simple picture of what you might think of as a standard way of doing speech signal processing in the beginning of the first stage of a speech recognition system, which I guess most of you, if not all of you, are very familiar with already. You take a short segment of speech, typically 25 milliseconds. You assume that over that 25 milliseconds period, the frequency structure of the speech is relatively stable, that the articulators haven't moved that much during that period. You apply some sort of window to smooth the edges to avoid frequency issues. You apply a Fourier transform, you take the amplitude, you throw away the phase information, and then you take the logarithm. And then you end up with something which, in an ideal world, might look a bit like this, some sort of estimate of the short-term frequency spectrum of the speech. And then we convert the frequency axis onto a MEL scale, onto a perceptual scale, because we're trying to take account of our knowledge about human speech perception. And we do that by basically taking weighted averages of our measured spectrum with a set of triangular filters, with critical band filters. And so the output of that is a vector, and the nth component of that vector then is basically the result of taking the nth window, multiplying that frequency spectrum by that window, and then taking an average. And then we do a cosine transform. We throw away the upper cosine coefficients. We add the delta and the delta squared parameters, the velocity parameters and the acceleration parameters, and then we get what you might think of as a standard representation, which we use for speech recognition, which in HDK, for example, is referred to as NFCC_D_A. But it's basically the lower order MEL frequency Kestrel coefficients plus velocity and acceleration parameters. And we might just take one of those feature vectors, or we might take a whole sequence of them as the input to our speech recognition system. So, the first place we're going to observe a mismatch is here, because if the children have a shorter vocal tract, then this frequency structure is going to be shifted for children's speech relative to adult speech. So, and that's what this picture is supposed to depict. So there are two issues here. First of all, because of the shorter vocal tracts of the children, the frequency structure in the bottom spectrum, which is supposed to represent a child's speech spectrum, will be shifted up the frequency axis compared to the adult spectrum. And if we do any sort of bandwidth limitation, so for example, we might decide we're only going to look at frequencies up to 4 kilohertz, then that may be enough to capture all of the relevant structure in the adult speech spectrum, but it may be that we lose some important structure in the child speech spectrum. So we've got two issues. One is compensating for the difference in vocal tract length, and the other is bandwidth limitation, which might actually remove some important information in the speech spectrum for children's speech. So this is actually rather just a schematic. This is actually some real data. This is some formant frequency estimates for adult speech and children's speech. This bottom quadrilateral is an estimate of formant frequencies, I think, from the Abbey corpus, from Standard Southern English in the Abbey corpus. And this top quadrilateral is an estimate of formant frequencies for various vowels from children in the PF star corpus. PF star corpus is a corpus of children aged between about 5 and 10, recorded as part of the PF star project, which was an EU project. And you can see that both F1 and F2 occur at much higher frequencies for the children's data than for the adult data. So that's just reflecting the picture that I showed you with the sort of schematic spectra earlier on. So the standard way to compensate for that problem is to use vocal tract length normalization, which is a technique which has been around since the late 1990s. And basically what you do is you try and compute a warping function, which I've drawn in green in this diagram here, to optimally align the adult speech spectrum with, in this case, the child speech spectrum. There's no fancy algorithm for computing the best warping factor. You typically do it by exhaustive search. So you have a grid of possible slopes of that warping function that you might consider, and you basically compute the probability of your unknown utterance warped with different warping factors, and you choose the warping factor which gives you the highest probability. That's the standard way of doing this method. Okay, so once you do that, for example, during training, you would use all your data to build a model, which I might call M0. So that's an acoustic model based on the unwarped data. Then for each training utterance, you search all of your possible warping factors, and you find the warping factor, which I've called alpha sub s, for which the probability of the warped data given the model is maximized. You do that using a grid search. You train a new set of models using the warped training data, and you keep on doing that until the process settles down. And then in recognition, given an unknown utterance, and your model set, you calculate again the warping factor, which gives you the highest probability, and then you apply that warping factor to the data, and that will lead to an improvement in performance. In reality, this process is typically implemented by modifying the positions of those triangular filters in the Davis and Mermelstein triangular filter bank. So that's focal tract length normalization. The next issue is the higher pitch, the higher fundamental frequency in children's speech. So what I've got here is a very simple representation of the source filter model of speech production. I've got the signal from the vocal folds on the left-hand side being passed through a vocal tract filter, and the output is speech. And then I've got the corresponding frequency domain, very simplified version of that story in the middle, which is, here's the excitation spectrum, the spectrum of the excitation, which you can see is basically a decreasing sequence of harmonics. You multiply that by the response of the vocal tract filter, and the output which you observe is a sort of sampled version of the spectrum. In fact, what you get is a sort of wavy version of the spectrum, which looks like a noisy version of the spectrum, but is actually the result of the convolution of the excitation signal with the vocal tract function. If the speaker is a child, then the fundamental frequency will be higher, so the gap between those peaks from the excitation signal will be smaller. 1 over the gap will be bigger, so the gap between these harmonics will be greater. And so when you multiply the decreasing sequence of harmonics by the response function of the filter, then what you're going to get is a much more coarsely sampled version of the spectrum. Now, the reason that's a problem, oops, oh, how would that work? Okay. Right, the reason that's a problem is because if you look at the standard Davis and Mermelstein triangular filter set, which we use to convert the Hertz frequency axis into a perceptual frequency axis, these are critical band filters. And a critical band is about 100 mels, and for frequencies less than a kilohertz, 100 mels is approximately 100 hertz. And so these filters at the bottom end of the filter bank have an equivalent rectangular bandwidth of about 100 hertz. And if you think of the previous picture where the gap between the harmonics can be anything up to 300 hertz, the position of the harmonics inside these filters is fairly arbitrary. And that means that when you apply this process to children's speech, the values you get in the low components of the MEL spectrum are very noisy. They're very variable, and that's because they depend on the exact positions of the harmonics relative to the positions of the filters. That leads to variability in the low frequency part of the MEL spectrum, and that in turn leads to variability in the high Kepstrel coefficients. So if you apply this process to children's speech, what you will observe as a consequence of the higher fundamental frequency of the children is much larger amounts of variability in the high order Kepstrel coefficients, and that leads to increased speech recognition errors. There's been various approaches to trying to solve that problem. The first one is an explicit method, which basically uses a method of speech synthesis, SOLA, to try and modify the speech of the actual test signal. But a much simpler solution was a solution proposed by Shweta Ghai in her thesis in 2011, which is simply to increase the bandwidth of the low order filters. So basically you modify the Davis and Mermelstein filter bank so that any filter which has an equivalent rectangular bandwidth of less than 300 hertz, you increase the width of the filter so that bandwidth becomes 300 hertz. That has the effect of smoothing the bottom end of the spectrum and removes some of the effects of the high fundamental frequency in children's speech. Another approach to all of this is to try and do age-dependent modelling. So a way of dealing with the variations as the age of the children changes is to build explicit models for different age groups. But the problem there is that no matter how big your corpus is, as soon as you start partitioning your corpus according to different ages, then you find you've got very little data left. You've got this trade-off between a better match between the test data and the training data, but reduced training data for any particular model. And then another, the alternative is you build age-independent models, and then you try and use some of the standard adaptation techniques that people have developed in the context of hidden Markov models, things like maximum likelihood linear regression, map adaptation, constrained maximum likelihood linear regression, to try and make the children's data look more like the adult data. And in cases where the training corpus is biased towards adult speech, you tend to get good results on adult test data, and you get better models, better performance on child speech than would if you hadn't done this adaptation, but it's not as good. It doesn't work as well as it does on the adult speech. So an example of that, but if you look at Alenius and Blomberg 2005 or Girosa and Giuliani 2009, there are lots of results of people trying to apply these standard adaptation techniques to children's speech. So what I've got here is some experimental results. I'm going to be very brief with experimental results. I'm not going to explain to you in great detail how the experiment was performed, but I'm going to give you a reference so you can see where to go if you want to find out more information about the experiment. The results I'm going to show you, the purpose is just to give you an idea of what the benefits or otherwise of the different techniques that we're talking about are. So Shweta-Guy basically proposed this method for doing pitch normalization in her thesis, and she presented these results. So we've got results on connected digit recognition and continuous speech recognition for children's speech. And these are the baselines down the left-hand corner under default. That's the standard system without pitch normalization. And the right-hand column in both cases is the result of doing pitch normalization. And so you can see as you move from the left-hand figure to the right-hand figure, you observe a small improvement, but it's consistent improvement in recognition accuracy, or a consistent decrease in word error rate by applying pitch normalization. You get a much bigger improvement when you apply vocal tract length normalization. So for the connected digit experiment, there's a 74% decrease in the error rate by doing vocal tract length normalization, and then a small additional decrease if you do both pitch normalization and vocal tract length normalization. So that's a 75% decrease in error with respect to the baseline system. And then for continuous speech recognition, a similar story. The default performance with no normalization is 56% error. With pitch normalization, you get a small improvement, 51% error. A much bigger improvement by applying vocal tract length normalization, and then again an additional incremental improvement by applying pitch normalization. So most people who try and approach doing children's speech recognition, at least until relatively recently, would begin by doing the combination of vocal tract length normalization and pitch normalization to try and compensate for these physiological phenomena which cause differences between children's speech and adult speech. Okay, I'm going to show you these results. These are a bit off track, because these are some results of not speech recognition experiments, but speech detection type experiments. And these are some results from one of my students, Syed Safavi at Birmingham. And I'm going to show you two results. I'm going to show you results for speaker recognition, and I'm going to show you results for gender identification, both from children's speech. And the way to interpret these graphs, forget about the colours, just concentrate initially maybe on the black histogram. And these are basically the results of applying, in this case, speaker identification, but just using a small subband of the frequency spectrum. So this first column here corresponds to the first 4 filters of the Davis-Mermelstein system. The second column will be filters 2 to 5. Here's filters 5 to 8, 9 to 12, and then 21 to 24. So what we're looking at is the power of different subbands for doing speaker identification for children's speech. And the different colours correspond to different age groups. So the black corresponds to the older children, the 7th to 10th grade children. The green is the 3rd to 5th grade children. These are American children. And the blue curve is kindergarten to 2nd grade. And this is a fairly standard picture. This is what you'd expect. You see best performance for the older children. And if we had some adult performance here, you'd see this graph converging towards adult performance as you get towards the older children. And you see gradually degrading performance as the children get younger, so between the blue, the green, and the blue curves. Now, the interesting thing about this is that the picture is pretty much uniform across the whole of the frequency range. You're seeing a drop here in performance according to the age of the child, but the effect of the age of the child seems to be pretty much the same for the low frequency subband as it is for the high frequency subband. You're also seeing that the low frequency information and the high frequency information, those are the places where the most information is for speaker ID. Contrast that with this picture here, the next picture. This is gender identification. And here you see quite a different sort of picture. Basically, the horizontal axis is the same. It's indexing these different subbands. Confusingly, the green curve is now the oldest children. The blue curve is the blue columns are the middle-aged children, and the black columns are the youngest children. And what you see here, ignore the red lines to start off with, is that up here you see relatively small differences between the performance for the different age groups, whereas down here you're seeing huge differences in performance between the different age groups. The red curves are what happens if you apply pitch normalization to this experiment for the younger children. And you can see if you apply that spectral smoothing, the pitch normalization that I've described, then a lot of the poor performance for the black curves for the youngest children disappears. So what you're seeing here is if you're trying to do gender identification, where the variation in fundamental frequency between kids is noise, it's spoiling your experiment. If you apply pitch normalization, then the performance is raised hugely for the youngest children. But if you go back to the previous curve, the speaker ID curve, for speaker ID, pitch looks like it's a characteristic of that child. It's useful information for doing speaker identification, and you don't see that degradation of performance for the lower frequencies as a function of age for the speaker ID. So I think it tells us something about, maybe it's obvious to everyone, but it wasn't so obvious to me. It seems to imply that for a particular speaker, the fundamental frequency is relatively consistent in that it provides a useful cue for doing speaker identification. But if you're interested in gender identification, then it's definitely noise, and you need to normalize it out if you want to get decent gender identification performance. So again, it's sort of all part of the understanding of how fundamental frequency affects the different types of technologies that we're interested in. Another issue linked with the length of the longer vowel durations for children's speech is speaking rate. Children tend to speak much more slowly than adults, and so another obvious approach to normalization for children is to try and do speaking rate normalization. To try and speed up the children's speech to get a better match with the adult speech. And that gives you a similar sort of improvement to the improvement you get with pitch normalization, a fairly modest improvement. I guess the interesting one with this one is that because you're throwing away data, you're probably making the data more consistent with the assumptions that the HMM is making about independence in the time series. And it's difficult to say whether the improvement you get by speaking rate normalization is really due to speaking rate normalization, or is it just because you're improving the fit with the assumptions that the HMM is making about frame-wise independence. Okay, so those are some basic results, some basic things about speech recognition for children. So here are some questions. So the first question is speech recognition uniformly difficult for all children, or is it the case that there are some children for which it's very difficult, others for which it's not so difficult, and when we get the average, we get the sort of performance that we observe? The second question explicitly is what's the effect of bandwidth on speech recognition for children's speech? And the third question is recognition of children's speech inherently difficult? And a way of measuring that is to say, is it also difficult for people to do? Are young children more difficult to recognize than older children? So I'm going to address each of those questions and provide you with a little bit of evidence to back up my claim. I'm going to talk about some specific experiments on some specific data now. This is a British English child speech corpus that we have. It's called a PSR corpus, the first one. PSR stands for primary school reading. And it's the corpus which we collected back in the 1990s to support the work we'll be doing then with the local education authority on pronunciation training for children. Then the next one is called Talking and Listening Books. This is recordings of 5 and 7-year-olds actually talking to a computer, basically a reading tutor. We've got recordings in London, Staffordshire, Edinburgh, Glasgow and Malvern. And the final one is the corpus recorded under this PF STAR project. It's 150 children aged between 5 and 12. And we've also got corresponding non-native English recordings from the Italian, German and Swedish labs which were involved in that experiment. But I'm not going to use those. I'm just going to focus on the native speech. So the first question, is speech recognition performance uniformly poor across all children, or is it just poor for certain children? And these results here suggest that it's the latter. So I sort of skipped over this when I talked about this corpus, but if we go back to the PSR corpus, we've got basically separated out 3 different bits of the corpus. So PSR1 is 5 children aged 5 to 7 whose teachers judge them to have very good pronunciation skills. PSR2 is children with varying pronunciation skills. And PSRA is a matched corpus which we created from adult speech. So this is adults saying exactly the same vocabulary as the children speak. And this is the results of experiments on those different bits of the corpus. The horizontal axis is bandwidth, so the graph showing the effect of bandwidth on speech recognition performance, and the different curves are basically performance for different types of speakers. So if we start off with this one, this curve here, the bottom one, this is the performance for adult speech. So this is adults speaking exactly the same vocabulary as the children spoke in the PSR corpus. And you can see there's definitely a bandwidth effect. You can see that up to about 4 kilohertz, the performance is relatively constant, but then as soon as you restrict the bandwidth below 4 kilohertz, you can see huge increases in the ASR error rate. This top curve is exactly the same experiment, but for children, and these are children whose teachers judge them to have poor performance. So these are the children who would be the subjects of pronunciation training aids, for example. And you can see that the basic performance, even at 8 kilohertz, is much poorer for these children. Whereas we're talking about error rates around about 20% here, we're talking about error rates 100% greater for these children. And you can also see that with children's speech, the error rate only stays constant up to about 5 or 6 kilohertz, and by the time you get to 4 kilohertz, you're starting to see increases in error rate just due to the bandwidth restriction. And this middle curve, this is children whose teachers judge them to have good performance. And the interesting thing about this is between 8 kilohertz and about 6 kilohertz, there's very little difference, or no real difference, between the performance on those children and the performance on the adults. These are matched systems, so the adult system is trained on adults, the child system is trained on children. And so this result suggests that it isn't the case that speech recognition is difficult for all children. It's difficult for certain children and not so difficult for other children if you have a matched system. And the children that it's difficult for are exactly the ones you'd expect. It's the children whose teachers, who the adults associated with them, would also judge their performance to be poor. So it's a small experiment, but I think that's the conclusion I would draw from that. Okay, so here are some conclusions from that experiment. There seem to be correlations between human judgment about pronunciation and the performance of speech recognition systems. For bandwidths greater than 5 kilohertz, the performance that we got for adults and for children to judge to have good pronunciation is pretty much the same. But the speech recognition performance for children's speech deteriorates for bandwidths less than 6 kilohertz rather than sort of 4 kilohertz for adults. And for 3 kilohertz bandwidth, the word error rate for children is 40% greater than for adults. So going back to that first experiment I showed you, the first paper by Jacobson and Wilpon, that will have been affected by the fact that they used telephone bandwidth speech in their experiments. So that will have contributed to the poor performance they had. Next question, is children's speech recognition inherently hard? And there are various studies of human speech recognition. There's an old study from 1997 by Richard Lippmann. And in those days, he claimed that for adult speech, computer error rates typically were an order of magnitude greater than human error rates for adult speech. One of my own students did an experiment back in 2007, Shona Darcy, on comparing human word error rates for children between aged 6 to 12. We got a human word error rate around 3.6%, and much larger computer word error rate around 70%. Valerie Hazan at UCL has done experiments on speech from 13-year-olds and demonstrated it's less intelligible than adult speech. So there does seem to be some evidence that children's speech is more difficult than adult speech. This is one of Schoner's results. This is human performance. So this is human recognition of children's speech. The different curves, the dotted curves correspond to different age groups, and the solid curve is the average. And so by the time you get to the diamond curves, ages 10 to 11, then you can imagine that that's sort of converging to what you would expect for adult speech. So this shows you quite clearly that the performance of human listeners on children's speech at different ages degrades as the age of the child decreases. So the speech recognition rates for the 6 and 7-year-olds are much poorer than the recognition rates for the 8 and 9-year-olds and the 10 and 11-year-olds, and therefore by implication for the corresponding data from adults. You can also see a similar effect to the ones you saw for computer speech recognition in terms of bandwidth, that as the bandwidth decreases, then when you go below 4 kilohertz, you see serious degradation in the performance for human listeners as well as for computer listeners. So that's the second thing. It does seem that child speech is inherently difficult. People find it difficult to recognize as well as computers. So here's a summary then. So, a summary so far. There are several of these summaries so far. I think we better get a move on. So I think there's been good progress since the mid-1990s on adapting adult speech recognition systems to work with children's speech. Combinations of things like vocal tract length normalization, pitch normalization, speaking rate normalization, and generic normalization techniques have raised the performance of adult systems on children to be comparable with what you would get with matched systems, but the performance is still poorer than you'd expect in typical adult ASR. It appears that the large error rates for children's speech are not uniformly distributed across all speakers. Some children are much more difficult to recognize than others, and it's those children that are contributing to the high error rates. We understand the bandwidth effects. If you do children's speech recognition using telephone bandwidth, for example, you will get an inherent error rate due simply to the bandwidth limitation. And we know that children's speech is inherently more difficult to recognize. Even people find children's speech more difficult than adult speech. So that's a summary so far. Right, so I thought, sorry, Obama is just someone whose picture is easy to get. So I wanted to make a point here. So this is Obama as an adult, and this is Obama as a child. And I think everything I've said so far suggests that as far as speech recognition is concerned, this is what speech recognition thinks Obama as a child was like. It's basically a small version of the adult. Okay? It's a child as far as speech recognition is concerned, so far, is a short, squeaky adult. Okay? And there's no real effort to accommodate anything more subtle than that in the techniques that I've talked about. So maybe the other objective would be to shift this arrow from the vertical to a sort of diagonal. Right, so the next thing is, what's the state of the art for children's speech recognition? I'm going to talk about two papers. These say nothing to do with anything that I've done. These are things which were presented either in InterSpeech last year or in journal papers since then. And as you would expect, there have been serious improvements in speech recognition for adult speakers over recent years by replacing Gaussian mixture models with deep neural networks to calculate the state frame probabilities in a hidden Markov model system. And so what about applying these to children? And there are two sort of conflicting, not exactly conflicting, but two different studies which I'm going to talk briefly about. One is by Serizel and Giuliani, and one is by Liao et al., and that's the paper from Google. So the Giuliani paper, the Serizel and Giuliani paper, it's basically Italian speech, it's Italian read speech, adult read speech and adult broadcast news data. And their paper is about whether it's beneficial to include the types of normalization techniques that I've described up until now in a DNN-based system. Because, I mean, there would be an argument which says that you don't need to do those types of normalization because the DNN will learn these differences, will learn to accommodate these differences. So then we look at a whole range of different methods for incorporating vocal tract length normalization into DNN-HMM systems. They look at conventional methods, the method which I described previously, where you try and choose the warping factor according to the warping factor which maximizes the probability of the warped data. They use a deep neural network to estimate the warping factor, the vocal tract length normalization factor. And then finally, they produce a vector of posterior probabilities over the range of different warping factors that we typically consider in the grid search. And their result is that in their DNN system, vocal tract length normalization gives reductions in phone or word error rate of up to 34%, respectively 12% on child speech. The best performance they observe in all of their experiments is 11.3% phone error rate, 10.8% word error rate for child speech and adult speech. So these are the figures for child speech. The figures for adult speech are in brackets, but when you look at the paper, they're not actually comparable. The child speech are on these simpler corpora, and the adult speech results are on broadcast news data. So they demonstrate significant improvements in accuracy by doing explicit types of normalization, which I've talked about up until now, and incorporating those into a DNN-based system. And that contrasts with the next paper, the second one, which is the Google paper, which was presented at the special session of Interspeech last year on speech recognition for children. And well, let me talk about their conclusions first. They conclude they get no benefit from vocal tract length normalization and no benefit from the sort of spectral smoothing type of methods that I described for doing pitch normalization. They look at different types of neural network-based systems, and they're talking about a very large vocabulary system, and they get a best performance of just over 10% word error rate. They have a huge amount of data. They have recordings of voice search traffic. They have something like 2 million utterances, which I tried to calculate it out from what the information in the paper. I think it's about 1,200 hours of data. They have a DNN system which basically tries to classify each of the elements of voice traffic as whether it's child speech or adult speech, because they don't know. They have to just use some sort of automatic classification method. So they separate the child speech from the adult speech. They throw most of the data away and just keep the child speech. They add various noise conditions to the data to try and simulate noisy data, and then they train up their DNN system using that data. And they observe no benefit from using VTLN or pitch normalization. And that performance, I think, is pretty spectacular, actually. I think that's very good for children's speech. However, so there's certainly significant improvements using DNNs, and I think that last result is really impressive, 10% word error rate, very large vocabulary, natural speech, but we don't actually know the ages of the children. We don't know the range of ages of the children in the experiment. We know their fundamental frequencies, but we don't know the actual ages of the children. And the age of the children, of course, is important. If those children are 5- and 6-year-old children, that's a much more difficult challenge than if those children are sort of 7-, 8-, 9-year-olds. In the second study, the normalization techniques that I've talked about, vocal tract length normalization, pitch normalization, don't appear to be advantageous, but that seems to be if you have a very large amount of training data. But we don't know how variable that data is. It may be that data is from a fairly homogeneous set of ages, in which case you'd expect those types of normalization to be less useful anyway. But the bottom line is there are no public large corpora of children's speech available to try and replicate that sort of research at the moment. And then Cirizel and Giuliani, they showed that the system isn't matched, and you have much less child-specific training data, then normalization techniques can be useful, the sort of normalization techniques that I've talked about up until now. So that's, I think, where we are. I don't think there's been very many advances since then. So that's pretty much the state of the art for speech recognition for children at the moment.
Excuse me, can I ask, do you make the presentation, or should I wait until the...
I don't know, what's the protocol?
So I want to.
Okay, go on.
Okay, so I'm wondering whether the difference between these two systems come from, say, the use of convolutional neural network as an input. Because convolutional network will extract some invariant features rather than, say, the variant features. So I think the DNN-based system doesn't use a convolutional neural network, but DNN-based system uses a convolutional neural network. So I think it will automatically normalize I think it incorporates vocal tract length normalization as a neural network.
I think, you probably know more about these different types of network than I do. I think the explanation is that, I think for both types of neural network that they use, they see no real benefit from doing these normalization techniques. So I think the point is that, first of all, their data is much more homogeneous, I suspect. I don't know what ages of children use voice search, but I suspect not many 5-year-olds do voice search, but I suspect a lot of 10 and 11-year-olds do, for example. So we don't know how homogeneous their speaker set is. And if the speaker set is relatively homogeneous, you wouldn't expect to get so much benefit from these types of normalization. And they have a huge amount of data, so they might well be able to learn these normalization techniques if they're necessary. Whereas in the other experiment, the recognizer is trained on adult speech, and therefore there is a mismatch between the training data and the test data, and therefore you would expect to see some sort of benefit. I think the interesting thing in the first study, the second one I'm talking about now, is that they look at different ways of incorporating that normalization information into the recognizer. And for example, the incorporation of a set of posteriors of different different normalization factors, different warping factors, is a bit like putting something like an I vector in with the acoustic input to tell the recognizer something about the speaker that it's trying to deal with. So I think that's an interesting area which could bear a lot more investigation. But I don't think the main difference is the fact that the subtle differences between the different neural networks.
Thank you.
Thanks. Okay, so the last bit of the talk, which I'm going to have to get a motor on, I'm going to talk about maybe looking at ways to try and incorporate the fact that we're dealing with children, that children are actually different to adults. They're not just small, squeaky adults. And one area where children differ from adults is young children in particular, they're learning language, they're acquiring language. And so the final question I want to look at is something which we've been working at more recently, is how does language acquisition, how do the phonological type of processes associated with language acquisition affect speech recognition for children? And there's lots of literature on this. If you go into the literature, in the speech therapy literature, you will find lots of information about the rate and the way in which children acquire language. Now, I'm not going to go through there because I think I'm running a bit late. So I'll go straight to the next picture, which is a graph. And this is a sort of summary from a couple of those papers. This is about consonant acquisition in children. So this is the percentage of consonants used accurately by 75% of children at different ages. So the horizontal axis is the age of the child. The vertical axis is the percentage of consonants that 75% of children are using accurately at that particular age. And you can see that things begin to settle down around about 7 and 8. And so up until 7 and 8, there are going to be effects in the child's speech, certainly in a proportion of the children's speech, which reflect language acquisition type issues. And as the children get younger, then the proportion of those effects in the speech is likely to increase. Oops. So one of my students, Ava Fringy, who I'm going to cite the paper in a few moments, has done a survey of some of these papers and come up with a list of phenomena that one might expect to observe in the speech of young children. And then we've been looking to see how much evidence there is that those phenomena are affecting the performance of the speech recognition system. So these are things like voicing, peach being pronounced as beach, fronting, so key becomes T, gate becomes date. All of these sort of simplified articulation strategies that young children use when they're still acquiring the language, and you would expect those phenomena to be reflected in the output of speech recognition systems. So Ava looked at 4 different papers, 4 different studies, and from those studies she came up with this table, which is basically a table of the ages at which you'd expect children to stop exhibiting particular types of phonological phenomena in their language acquisition. And so everything from voicing to stopping, and so again, the vertical axis now is age, the horizontal axis is the different phenomena, and the Y's basically indicate when a particular child at a particular age would be expected no longer to be exhibiting that particular phenomenon. The ones circled in red are phone substitution type phenomena, and those are the ones we've looked at. So the question we've been looking at is whether you can attribute a large number of the phone substitutions in speech recognition errors for children to these types of phonological process, in particular for the youngest children. Now the problem with this is that if you look at those types of error, car being, the T, K being misrecognized as a T, etc. These are exactly the sorts of errors that speech recognition systems make anyway. So somehow you have to separate out the instances of those substitutions which might be due to these phonological effects associated with language acquisition in young children from the background error rate which you would expect for those phenomena anyway. And we have a simple statistical test to do that. So we take a confusion matrix, a phone confusion matrix from an experiment where we don't expect to see any of those phenomena. So for example, that might be an adult phone recognition experiment. It might be timid, for example. And we use the parameters in that confusion matrix as the parameters of a statistical model. And the null hypothesis is that the confusions that we see in the ASR phone confusion matrix for children's speech are random variations that we see in the baseline confusion matrix, in the timid confusion matrix. And we basically identify a confusion as being statistically significant if the probability, according to the adult data, of that number of occurrences of that phone substitution, if the probability of that number of occurrences of the phone substitution, if the probability of the number of occurrences which occurs is greater than, is less than 0.05, then we say that that's statistically significant. Let me say that again. So we've got a standard phone confusion matrix which has been derived from a corpus like timid, and we assume that that is not exhibiting any errors which are due to these phonological processes associated with language acquisition. If we use that as the parameters of a statistical test, for every particular substitution that occurs in some other data, we can work out the probability of that number of substitution, of that particular phone substitution occurring based on the statistics in the baseline confusion matrix. And if the probability of that number of that substitution occurring based on the statistics in the baseline, the standard confusion matrix, is less than 0.05, then we say, well, that's not chance. We can't explain that as just a random variation of what we see in timid. We say that's significant, that's statistically significant. So the experiment is run a phone recognition experiment on children's data, create the confusion matrix, look at the number of confusions which occur, the number of times each confusion occurs, and then look to see if you could explain that number of confusions as being a reasonable random variation of what you see in the adult data. Yeah, I'm almost done. And the answer is disappointing. So this is the result. This was at InSpeech last year. For 5 to 6-year-old children, where you would expect those phenomena still to be visible, only 7% of the errors that we see, the phone recognition errors that we see, are predicted by these developmental factors. That's the first thing. The second thing is, at least you'd expect that number to decrease with age, but in fact it doesn't. Okay? It seems to stay pretty much constant across all the ages that we looked at. Now, we have conflicting explanations of that. One explanation is if this phenomenon is actually happening, then high speech recognition error rates are going to sort of obscure that phenomenon. You're not going to be able to see it so easily. So as the child gets older and the speech recognition error rates get lower, you might be able to see these phenomena happening more easily. And that might compensate for the fact that they're not happening as much. There's another hypothesis which says that, okay, these phonological processes are supposed to have been resolved by the time the child is age 6 or so. But is that really the case? If a child, for example, is using a W instead of an R when they're very young, and then we judge they're not doing that later on in life, is it the case that their R's are still slightly W-like, and is that still causing issues to speech recognition? So that's another question. We don't know the answer to that. So
Martin, is that LVCSR you're running at that stage, or is it phone recognition?
It's phone recognition on it's American recordings of American children done by Disney, and they're basically it's not read speech. It's them responding to a particular game.
The recognizer itself, is it a phone?
It's a phone recognizer.
Okay, thank you.
Sorry, it's a phone recognizer. Okay, and I think that's so. It seems that we cannot attribute a large number of the errors that occur in the speech recognition for young children to these types of effects. And it seems to me that's sort of consistent with some other results which have occurred over recent years, which have sort of been puzzling. So another way of looking at these phonological processes would be to say, let's use them to modify the pronunciation dictionary. Because if we can modify the pronunciation dictionary using known mispronunciations, which we might expect children to make, then we'd expect performance to go up. And when people do that, they get an improvement, but it's incredibly modest. This is a paper from Alex Petanianos at the WOCI meeting in 2014 in Singapore. I'm not going to go into any of the detail, but the middle column, the second column is the baseline performance, and the third column is the performance you'd get when you modify the pronunciations. And they're not even using modifications based on these rules, they're using measured modifications from the speech. And you see very, very small improvements in performance given the level of error rate that you've got from modifying pronunciation dictionaries. Here's another experiment which we did a number of years ago. We took two speakers. The first one was judged to have very good pronunciation, the second judged to have very poor pronunciation. We hand transcribed their data, and then we used the hand transcriptions to create a customized dictionary for that child. And these are the recognition errors for the standard dictionary and the customized dictionary. Sorry, these are accuracies, they must be, because it should at least be better. Yes, that's right. Okay, but it's a minute improvement. If you've got a 35% accuracy and you do something, you really hope to get a better improvement than simply bumping it up to 43%, I think. So I think all of this seems to imply that the errors we're seeing in children's speech are not easily explicable by regularities which you can explain at a sort of symbolic phone level. And I think I'm going to skip that one, and I'm going to move on to the conclusions, because I think Roger's going to become irritated in a moment. Right. Computer speech recognition for children is more challenging for children than it is for adults. Most of the research is focused on normalization techniques to make adult speech recognition work on children's speech. And the reason for that is that there are lots of adult speech recognition systems out there. There are no large public corpora of children's speech. And by work as well as adult, I mean achieve the same level of performance you might expect from a matched system. And these techniques which I've talked about, vocal tract length normalization, pitch normalization, and generic adaptation techniques, they largely deliver the objective of getting the performance of adult systems on children to be as good as the performance of child-trained systems on children, which is still not as good as adult-trained systems on adults. Most speech recognition systems still treat adult children as short, squeaky adults. There have been significant performance improvements by applying DNN-HMM systems to children's speech, but the results are not entirely clear, and for most researchers, the absence of large public corpora of children's speech is going to be a real issue in this area. The phonological effects associated with language acquisition only appear to account for a very small percentage of phone substitution errors, even for very young children. You might expect much more than that. And similarly, modification of the pronunciation dictionary only results in very modest improvements in word error rate for children. I think there are lots of interesting challenges here. For example, in visualization, trying to understand what happens to speech as a child goes from very young age to older ages. We need visualization techniques. The problem is most of these visualization techniques need to apply to consonants, not to vowels. And I think there are some questions about symbolic descriptions of young children's speech and really how useful it is from a computational point of view. Right, I'll stop. Sorry, thank you.